Hi, welcome to my H5 lab report. For this lab, our objective was to become familiar with AC power and power factor correction for a load network. And so the tasks for this lab were to design a circuit similar to the sample lab circuit. This is what I designed right here. And then calculate the power factor and power factor correction for this load network. And then adjust the circuit so the power factor correction can be done with the capacitors we have available. And then try solve for this voltage and current and the complex power. For the circuit that I chose, we can find the power factor by using the source voltage and the load impedance, and then finding the VRMS. Since that's a sinusoid function, the VRMS is just VI divided by square root of 2, and then IRMS can be found by doing VRMS times Z load, Ohm's law. We can use this VRMS and IRMS to find the complex power. And with this, we can find real and absolute power to get the power factor. To find the capacitor that, when added in parallel, correct this power factor. This would simply be where the imaginary part of the impedance of the capacitor cancels out the imaginary part of the impedance of the load. And so, since we're working with admittances, this was done since admittance adds in parallel. The admittance of capacitor is just J omega C, and then isolate C divided by omega. And so the capacitance should be equal to the negative imaginary part of the load. And so the resulting capacitance would be 143 nanofarads roughly, but it's unlikely that I can replicate these with the capacitors I have available and adding them in parallel. And so the circuit must be adjusted. So I chose to adjust the frequency for simplicity, as I don't need to measure any more components or reassemble my circuit. And to find out what frequency to adjust it, I just took a capacitor that I had, measured it, and used that as my capacitor that I will be using. And so then I can calculate the frequency that would make the imaginary part of the load impedance plus the capacitor's admittance equal to 0. And this results in a frequency of around 2,347.5 hertz. And so I will be using the circuit plus the circuit with the capacitor added in parallel for the remainder of the lab. And so, first step, we calculated the power factor of that adjusted circuit using the same method we used back up here for the not adjusted circuit. Just to double check, we find that if you isolate the capacitance or solve for the capacitance, that would correct the power factor. It is in fact 33.98 nanofarads. You can find the current using Ohm's law, just the source voltage divided by the load or the total impedance. And then the voltage of the load is just, you can use voltage dividers. The results are summarized below. This is repeated for the adjusted circuit with power factor correction, i.e. the capacitor added in parallel to the load network. So the calculations will be the same for the power factor and current and voltage and complex power. But the only difference is that the new load impedance will have to include that capacitor added in parallel, as we did right here. So then we solved for the complex power, real reactive power, current and voltage. And to double check our work, the power factor is indeed equal to 1, which is what we wanted. So summary of the results again. Now for multisim, for the adjusted circuit, we can set up the oscilloscope and the voltage probes to measure the VRMS and IRMS. And we can use a different approach to find the power factor, complex power, and voltage and current. So, summary of the measurements. We can use this time lag to find the phase difference of the voltage minus the current, which is right here in radians. And then the power factor is just the cosine of this angle. These formulas were taken from the topic notes. And using this time lag, VRMS and IRMS, we can just calculate the real power, reactive power, and the complex power using these formulas. And then for the voltage load and current, source current calculations, they're slightly different from the analytical approach, since we have V after, which we measured, expressed that as a phasor domain. The voltage load would be the V before minus the V after the load, and the current is just source divided by total impedance. Same approach was used for the adjusted circuit with power factor correction. And so yeah, the same process was used using the time lag, VRMS and IRMS, and that voltage after result is summarized below, and now we have the physical build. I tried to build this as close to the circuit diagram as possible. The red and black wire are used to hook up the AWG, and we have blue wire just to measure the output signal, extra ground connection to reduce signal noise, and then that voltage just after the load network measurement. And in these measurements there will be some error, and we can use the same approach we used for the analytical approach. Again, we repeat this for the capacitor added in parallel to correct the power factor, and same calculations, but note that to get the error for the calculated values, I just used the brute force method, which I could scroll down to. I added the maximum error to the initial voltage as well as the time lag and the voltage measured amplitude, and then subtracted it from just the calculations that were done without this max error to get the error in all these calculations. And so the results for this try-solving method are summarized here. It can be seen that the calculated value and multisim values are quite similar, are almost identical in fact, but slight differences arise from the error involved in using the oscilloscope to measure the values, since they had to be manually placed and I'm not perfect, and I can't measure the exact point at which the voltage signal is at a maximum or when it crosses the x-axis. And it should also be noted that for the most part, in fact for all the values except the source current and voltage across the load, the multisim and calculated values fall within range of error of these values, indicating that, well, the error analysis that I use is probably an accurate representation of the error involved in the calculations. However, since these do not fall within range of error of these ones for both cases, it could suggest otherwise. I go on to explain that this could be a result of the voltage and current calculations being more sensitive to the error, non-accounted sources of error, compared to the other calculations. And then I go on lastly to talk about what the results mean. And it could be seen that the power factor is corrected, it's 1. The imaginary component of the complex power is essentially 0 with rounding error. And this is exactly what we want. We don't want any reactive power, as we are build on that apparent power. And this also corrected the out of phase current and voltage. As we can see right here, they're out of phase, whereas they're approximately 0. I mean, really small numbers. This is exactly what we want. We want that current voltage to be in phase so that the load network is constantly dissipating power. And thank you for watching. Hopefully I did a good job.